So this is section 6.2, which is about one-to-one functions and inverse functions. And the two are related, so it's important to kind of learn them together. But we're going to start with one-to-one. So a function that's one-to-one is one where each element in the domain corresponds to a different element in the range, meaning like x's can't repeat and y's can't repeat. So each x goes to exactly one y value, and each y value goes to exactly to one x value. There is no repeating. Graphically, you can kind of tell this with what's called the horizontal line test. You move a horizontal line over your function. If it touches more than once, then it's not one-to-one. If it touches only one time, it is one-to-one. But numerically, you can kind of see if a function is one-to-one just by looking to see if the x's repeat or if the y's repeat. So let's look at some examples here of this. So example 1 asks us to determine whether the following functions are one-to-one. Over here we have two sets of data that are related, age and HDL cholesterol. So we have 38 going to 57, 42 going to 54, 46 going to 34, 55 going to 38, and 61 going to 38. Since both 55 and 61 point to 38 here, this is not one-to-one. Okay. Now if 61 had pointed to a different number, like 36 or something like that, then it would be one-to-one. Each x would go to one y, and each y would go to one x. But here, both of these x's go to this same y, so it's not a one-to-one function. Okay. Example B here, we got just a set of points, -2, 6, -1, 3, 0, 2, 1, 5, and 2, 8. First thing, look for repeats in the x's. -2, -1, 0, 1, 2. Nope, x's are fine. Then look for repeats in the y's. 6, 3, 2, 5, 8. No repeats in the y's. Since x's don't repeat and y's don't repeat, this would be a one-to-one function. Okay. All right. Example 2 asks us to use the graph of the functions to determine whether the functions are one-to-one. So our first one is f of x equals x squared. Hopefully you kind of remember what that looks like. It's a parabola. Looks like this. So to test graphically if it's one-to-one, we are going to draw a horizontal line across and see how many times it touches. When I draw this across, you can see it touches 2 times, so this function is not one-to-one. For part B here, we have g of x equals x cubed. This function looks kind of like this. Okay. And again, to test if it's one-to-one, we hold up a horizontal line. Oops, that's not quite horizontal. Almost. There we go. Look how many times it touches. It only touches 1 time. So this is one-to-one. Okay, so pretty easy to test, not too bad. Now, why do we talk about one-to-one functions? Well, one-to-one functions are related to inverse functions, and we'll talk specifically how they're related in just a second. But let's talk about inverse functions a little bit. Okay. If you have two functions, f and g, such that f of g of x, which is the same thing as f composed of g of x equals x for every x in the domain of g, and g of f of x equals x, or we could say this as g composed of f of x equals x for every x in the domain of f. So if you have these two functions where this is true, where when you plug g into f, you just get x, and when you plug f into g, you just get x, then these two functions are called inverses. Now, what that really means is that the x values and y values switch. So what is an x value for f becomes a y value for g. What is a y value for f becomes an x value for g. Inverse functions just mean x and y switch. That also means, though, that these functions that are inverses are a reflection across the line y equals x. Because the y and the x are switching places, y is equal to x and x is equal to y, and so it's a reflection across that line. Okay. So let's look at that. Here we have a function. It's listed as a set of points: -3, -27, -2, -8, -1, -1, 0, 0, 1, 1, 2, 8, and 3, 27. And it asks us to find the inverse of this function. Now, for inverses, x's and y's just switch. So this first point would become -27, -3. This second point would become -8, -2. This third point would become -1, -1. The fourth point would be 0, 0. The fifth point would be 1, 1. The sixth point would be 8, 2. And then the last point would be 27, 3. And that would be our inverse function. Okay. Because inverse really just means x and y switch. Okay. Now, when we talk about f and g being inverses, we usually, instead of writing f and g, we replace g with f with a little -1 exponent. This is read as f inverse. It's not f to the -1 power, it's f inverse. So we're saying we have a function f, and then we have its inverse, f inverse. So g of x is the same thing as f inverse of x. And so what that means is when we had f of g of x equals x, that's really f of f inverse of x equals x. And over here, when we had g of f of x equals x, what we really had was f inverse of f of x equals x. Okay? So just kind of remember that f inverse and g are kind of synonymous here because the idea is that they're both inverse functions of f. It's just different ways of describing it. So the next thing we're going to do is we are actually going to verify that two functions are inverses of each other. And the way we do it is by doing a composition, just like these that you see right here, okay, here, and over here. We're going to do these compositions, and we're going to see when we do a composition, do we just get x? If we just get x, then they are inverse functions. If we get anything else, then they're not inverse functions. Okay. So example 4 asks us to show that each function is the inverse of the other. F of x equals 3x plus 2, g of x equals x minus 2 over 3. So the first thing I want to do is I want to do a composition f of g of x. So what that really means is I have f of x minus 2 over 3, because that's what g of x is. So I'm going to take x minus 2 over 3, and I'm going to plug it into the f function. So I'm going to have 3, and then instead of x, I have x minus 2 over 3, and then plus 2. Now the first thing that can happen here is this 3 and this 3 can cancel out. So we end up with x minus 2 plus 2. And then the minus 2 and the plus 2 can cancel out, and so we just get x. Since we just got x, that's a good sign that these two functions are inverses of each other. Right. Then we want to do the other composition. We want to do g of f of x. So that means we're doing g of f of x is 3x plus 2, so fill that in there. So g of 3x plus 2, plug 3x plus 2 into this function, so we'll have 3x plus 2 minus 2 over 3. The plus 2 and the minus 2 cancel out, so we end up with 3x over 3. 3x divided by 3 is just x. So we got just x again. Since both of these come out as just x, we can say that f and g are inverses. If either one of these had come out as something else, they weren't x, then we couldn't say they were inverses of each other. We can only say they're inverses if it comes out as x. Right, let's do another one with a slightly different notation. Example 5 asks us to verify that the inverse of f of x equals x to the third is f inverse of x equals the cube root of x. So the first thing we're going to do is we're going to do f of f inverse of x. So that's f of f inverse. Our equation is the cube root of x. So we're going to be taking the cube root of x and plugging it into the f function. So we're plugging it in here for this x, so we're going to have the cube root of x, and that's getting cubed. What happens with a cube root and a cube? They cancel out, and so we just get x. So that one worked okay. What about if we go the other way? What if we do f inverse of f of x? Well, we'll have f inverse of f of x. Our equation for f of x is just x cubed. So we're taking x cubed and plugging it into f inverse. So we're plugging it in there for that x. So we're going to have the cube root of x getting cubed. What happens with a cube root and a cube? They cancel out, and so we just get x. Since they both got x's, we can say that f and f inverse are inverses. We did verify it. We did prove it. All right. So how do you find an inverse function? Look, we've talked about how you verify, how you prove that two functions are inverses. But how do you actually find one? Well, here's the basic steps for you. Step 1, replace f of x with y. Step 2, switch x and y. So every place you see an x, put a y. Every place you see a y, put an x. Step 3, solve for y. If it's not possible to solve for y, then that tells you that the function doesn't have an inverse. But if it is possible to solve for y, then the function does have an inverse. Step 4, if the function does have an inverse, replace your y from step 3 with f inverse of x. We can always check our answer and verify the results by doing our compositions and proving that they equal x. So let's do some examples here of that. So example 6 asks us to find the inverse of f of x equals 7x minus 5. First step is replace f of x with y. So we have y equals 7x minus 5. The second step is switch x and y. So I'm going to have x equals 7y minus 5. The third step is solve for y. So I'm going to add the 5 across. X plus 5 equals 7y. And then I'm just going to divide everything by 7. So I'll end up with 1/7 x plus 5/7 equals y. The last step is to replace y with f inverse. So we'll have f inverse of x equals 1/7 x plus 5/7. And again, you could check that you were correct by doing a composition between these two functions and seeing if it equals x. Right, let's look at example 7. Find the inverse of f of x equals x cubed plus 1. First step, replace f of x with y. So y equals x cubed plus 1. Second step, switch x and y. So x equals y cubed plus 1. Subtract the 1 over. X minus 1 equals y cubed. To get rid of a cube, we use a cube root. So this is the cube root of x minus 1 equals y. Last step, replace the y with f inverse. So f inverse of x equals the cube root of x minus 1. Okay, not too bad. And some of them are pretty straightforward to find inverses of, although there are complicated functions too. is occasionally a little bit harder to find an inverse of. Right, let's look at number 8. Number 8 asks us to find the inverse of f of x equals 5 over x plus 4. So first thing we're going to do is replace f of x with y. So y equals 5 over x plus 4. The second thing we'll do is switch x and y. So we'll have x equals 5 over y plus 4. Then we'll solve for y. So we'll take the 4 over. X minus 4 equals 5 over y. Then what I'm going to do is I'm going to multiply both sides by y. So I'm going to multiply this side by y, and I'm also going to multiply this side by y. So what I end up with is y times x minus 4 equals 5. And then I can divide both sides by x minus 4. And so I get y equals 5 over x minus 4. And then the last step, replace y with f inverse. So f inverse of x equals 5 over x minus 4. Not too bad. Alright. So, going back to one-to-one functions, we talked one-to-one earlier, and we talked about how we could use the horizontal line test to prove if a function was one-to-one. Now, here's how it relates to inverse functions. The only types of functions that have an inverse function are functions that are one-to-one. So if a function is one-to-one, it will have an inverse function. If a function is not one-to-one, then it will not have an inverse function. Now, sometimes we can take functions that are not one-to-one, and we can restrict their domain and make them one-to-one. That restricted domain will have a restricted inverse function. But if we don't, then the only type of function we can look at that has an inverse is a one-to-one. And so what we're going to do here in example 9 is we're going to look at some graphs of functions, and we're going to see, does this function have an inverse function? Now how we do it is we check, is it one-to-one? So here on example 9, it asks us, which of the following graphs represent graphs of functions that have inverse functions? So we're wanting to check, are they one-to-one? Well, to check one-to-one, we do our horizontal line test. So we'll draw a horizontal line on each one of these. Okay. On this one, how many points does it touch? It only touches 1, so that means it is one-to-one. So that means, yes, it does have an inverse function. All right, look at this one. How many points does it touch? 1, 2. That means it's not one-to-one, so it does not have an inverse function. Look at this one. It touches 1, 2, 3 points. Since it touches 3 points, that means it's not one-to-one, so that means it does not have an inverse function. And this one, look, it only touches 1 point, so it is one-to-one, and since it's one-to-one, it is an inverse function. Or it has an inverse function. Okay. So one-to-one is a characteristic that graphs can have, and it's an easy way to tell whether or not you have an inverse function. The next thing we're going to look at is graphing inverse functions. And graphing inverse functions is actually pretty easy. You remember how when we were solving equations we just switched x and y? Well, the same thing works here. If you're trying to graph an inverse function, all you do is you take the points on your original function and you just switch the x and y around. Okay. So let's look at an example of this. Oops. Alright, so there's my x-axis and y-axis. So they've given me a function here, and I'm going to take the points off of this function and make a little table. So this point is -3, -2. This point is negative 1, 0. And this point is 4, 2. And so this is for my f of x. For my f inverse of x, all I have to do is take these points and just switch the x and y around. So flip these around, this is now negative 2, negative 3. Flip this around, this is now 0, negative 1. Flip this one around, now it is 2, 4. And then you just plot those new points. So negative 2, negative 3 is down there. 0, negative 1 is right there. And then 2, 4 is up there. And then you just connect them together in the order that you plotted them. So negative 2, negative 3 to 0, negative 1. And then 0, negative 1 up here to 2, 4. And so that would be the graph of our inverse function. Okay. So here's my f of x, and here's my f inverse. Pretty straightforward, just switch the x and y. Okay. So our next one asks us to find the inverse of f of x equals x squared minus 1, where x is greater than or equal to 0. And then to graph f and f inverse in the same rectangular coordinate system. Consult the graph of f below as needed. So we have this graph here. This is a graph of this function, okay, x squared minus 1. But here's the thing. We have this stipulation right here. X has to be greater than or equal to 0. What that does is that actually eliminates part of this graph. And there's a reason why they did this. Right now, if we did a horizontal line test, how many times does it touch? It touches twice, which means that the function is not one-to-one, and so it's not going to have an inverse function. And they didn't like that. They said, okay, I don't want it to look like that. I don't want it to be not one-to-one. So what they did was they added this restriction. They said the x has to be greater than or equal to 0. And what that does is that cuts off this half of the graph where the x is less than 0. So all we have is where x is 0 and where x is greater than 0. So we just have this part of the graph. And when we just have this part of the graph, if we do our horizontal line test, how many times does it touch? It only touches one time now because we cut off this part of the graph. So since now it only touches one time, now it's only one-to-one, and so it has an inverse function. So that's why they included this stipulation. Now, you don't need to worry about that when it comes to graphing or anything necessarily, other than realizing that you're only going to be looking at the right-hand side of the graph. Okay? So when we make our table of values for f of x, we're only going to use points that are on the right-hand side here. So my first point is this point here at 0, negative 1. My next point is at 1, 0. And then at 2, it looks like 3. Yeah, 2, 3. And then at 3, it's kind of off the graph. If I plug 3 into this equation, 3 squared is 9, and 9 minus 1 is 8. So it would get 3, 8. So for our inverse function, all we need to do is switch around the x and the y. So 0, negative 1 becomes negative 1, 0. 1, 0 becomes 0, 1. 2, 3 becomes 3, 2. And 3, 8 becomes 8, 3. And so these are the points that we would plot. So this is going to be our f of x, which I think I'm going to draw in black. And then I think I'll do blue for our f inverse. So that way I can graph both of them in the same thing below. So here's my little grid. Let me draw in my x and y axis really quick. There's my x-axis. There's my y-axis. Okay. So I'm going to start with my original function. So I had 0, negative 1, and 1, 0, and 2, 3. And then 3, 8 would be off the graph somewhere, so it's going to kind of go up that way and keep going that way. So this is my f of x graph. For my inverse, I'm just switching the points. So I'm going to have negative 1, 0, which means I'll have this point right here. And then I'm going to have 0, 1, which is this point right here. And then 3, 2. And then 8, 3 is going to be off the graph somewhere. So it's going to go that way and keep going that way. And so that's my f inverse graph. So there's what it looks like when we graph both of those together. Now, this problem didn't ask us to, well actually it did, never mind. It asked us to find the inverse, so we need to actually find the inverse equation. So I'm going to do that down here. So first thing we'll do is we'll replace y with f of x, or sorry, replace f of x with y. So we have y equals x squared minus 1. Then we switch x and y, so we have x equals y squared minus 1. We add the 1 across, so we have x plus 1 equals y squared. Then we take the square root, so we get y equals plus or minus the square root of x plus 1. And then we need to decide, do we want the positive or the negative? If you look at our graph, the y values are always positive on this graph that we drew. So we do want the positive square root. So we just want y equals the square root of x plus 1. And then the last step is to replace y with f inverse. So f inverse of x equals the square root of x plus 1. So there's our equation that matches this graph right here. Okay. And so that is it for 6.2. As always, if you have any questions on any homework problems or anything, feel free to send me an email and I'll try to help.